first schedule this either or today or next or Thursday we are going to use this, so I will not spend the time in the class. I just give you the proof, and you can read for details how we get it. So I'm thinking we almost the middle of the October we have just in this chapter 3 now. So we need chapter 8, chapter 9, and at least the part of chapter 10. In particular, chapter 9 is important. So let me see. Let me first summarize a little bit what we have discussed the last time. That we are interested before doing the detailed solution of equation motion. We want to see the orbit, right? So analyze orbit. Orbit for continuous. And based on this different type of force and force, and then that means we have potential, then the initial energy and angular momentum, right? So example, we have the force according to negative 1 over r squared. In this type, potential is proportional to 1 over r, right? Negative. And in this case, we have the curve in front is like this, right? And then we have the depend on the initial energy. E1. Okay, the E2 is 0. And E3 is negative. Then E4 is minimum. So we have, in this 4 case we discussed, this one open, right? Open orbit, and which is a hyperbola. Hi. Then in this case, it's also open orbit, but this is a parabola. The third one is bounded, or depending on this bounded or closed, right? Bounded, closed. So that is the example EV. And for this one is circle, right? That is closed. That is a circle. This is a case, this type, right? So first one. Second one we discuss is the force is proportional to the negative 1 over r force power, or V is proportional to negative 1 over r cube, right? And in this case, this curve is like this. The curve. Yes. And you also got my email for this solution, right? Yes. Okay. Let me know if you have any questions. This one copy is the one which I have another copy. Yeah, this one we are going to discuss. So I'm provide this proof. I will not spend time in the class to the proof. Okay. So in this case, we also have just several cases for energy, initial energy E1. E2 is just equal to the minimum, so let's say E2. We discussed E3 only this case, right? We didn't discuss others. And 0, 4. Okay, so we just discussed this one, and we have a region 1, 2, 3. Right, so we have the others, and let you know, you as discuss yourself. So in this case, this one is bounded. I didn't give the orbital I want you to consider yourself. Bounded means is the orbit, right? Bounded orbit. And the region 2, we know that's forbidden, so region 3 is open orbit, and which is hyperbola. Hyperbola. Then the number, let me use this one since we keep continuing this today. We also consider another force which is like a hook. The force which is proportional to the negative this one. So for this one, we have this potential is also, the potential is proportional to is half of, if we have a K, right, square, or equal or proportional, right? So in this case, we prime is like this. We prime. Then the partial energy is only 2K, since this goes to infinite. Either energy is positive, another is go to the minimum, right? Okay, so we discuss the energy is equal to E1, which is positive. And we know we have two turning points, R1, R2 we discussed last time, right? So, and the details I will, like this, I will not discuss. So that is bounded or closed orbit, which is like an ellipse. So, as I said here, right, either this one, this is a bounded, means you can see this this always try to go to different position, but always bounded, not go over, but not close. This one is close, so we have two possible orbital for this case. Okay, and for this case, it is interesting since we know the F, right? So we know the F, R is the, okay, if we want to consider the vector, because it's really, so that if we decouple into the two components, Fx is minus k x and Fy is minus ky, right? That is if you decouple this one. So the force has two if we plot to this xy component. So what that means, if you're familiar with, you see the k, if I say kx, ky, in this case, kx equal to ky equal to k. And that kind of, this actually like along x we have simple harmonic oscillation, simultaneously we have along y simple harmonic oscillation with the same frequency, right? So that is this one is resultant of the two simple harmonic, resultant of two simple harmonic oscillation. That's a combination of this. And if you familiar this one, then we know this depend on, so that's like vertical, right? So depend on the orbital. And we say closed, right? But what type of shift to the orbital? Orbitals. Okay, so that depends on the phase. The phase is the phase between the x and y, right? Depend on this. So if equal to 0, you will see that is linear. Linear harmonic oscillator. Suppose it's x and y, so something like that. This case is when equal to 0. So like this linear shape of the oscillation. Then if this is equal to just perpendicular, so that is circle, and others is like a kind of ellipse, but over like these Jones figures. So that if the circle, let me just make this distance. This is this one. This is, and then others like. Something like this, right? These are Jones. So that really depends on the initial phase. That is particular case for this kind of potential. So you know the orbit, it is bounded, and whether it is what type of the bounded or orbital depend on this phase. All right. So now next one is another this case. So that is a case 1. Now we consider case 2. Energy just equal to the E2, which is V prime minimum at this position. So in this case, do the similarity we discussed in this case, right? And we didn't discuss this case, but I think you can understand yourself. So here, remember, in this case, R dot is 0 because this. You see here, this R dot is due to this difference, right? I didn't write down. Okay, I'll try to remind you. So now let me write down here. To analyze, we need some of the information. If you remember, energy minus V prime gave us this radial velocity, right? And the V prime minus V, that difference gives us this angular. Which is just L squared over 2m R squared. And if the difference between energy and real potential, that gives us the total kinetic energy. So by analyze this, we can know what kind of motion, right? So in this case, in circle, this just equal to energy equal to V prime, which is V prime's minimum here. So there's no radial change, that means it's a circle. And then the angular momentum here, for giving one, so that is also constant, right? If you remember, now R squared, so that is constant, since R naught is constant. Then keep it continue with this. So that is the circle. And in this case, we can also have this force. So because in this case, since F prime R, if you remember, we introduced a factorial potential. So that case in this here, right? That is derivative, that is extreme, 0. Then we know at this position, if you remember F prime is so F prime is equal to F at this position, and the plus L squared over M R Q, that is centripetal force, right? If that equal to 0, so we have the force, in this case, do the circular motion, the force, that centripetal force is equal to negative of L squared over M R Q, which is negative. So that is centripetal force. And we have just equal to negative or opposite direction of centripetal force. That is the real force. We keep this the particle through this circle. Okay, so that is the case 2. Now case 3. In this case, we want to consider additional for L equal to 0 case. We didn't discuss L equal to 0 here, but you can also think about if L equal to 0, what happened here, right? So let's discard this kind. So L equal to 0, let's see. The V prime equal to V, right? Because V prime, I didn't give even just remind V prime equal to, okay, let's see. If V prime equal to V plus this one, right? Okay. Square. And then if it is not, this is not, this is any case. So that equal to 0. Equal to 3. Because this term is 0, right? So in this case, you see the V prime curve is only this one. Then now we consider any case we have energy here. Okay, let's first look this what kind of motion, right? Let's look at the radial part. Let's just this one. E minus V prime equal to E minus V. So that is a half of M V square and also equal to half of M R dot square, right? Because now V prime equal to V, so that only this radial part. So R dot is not 0, but how about this theta dot? So V prime minus V equal to V minus V equal to 0. So no rotation, right? No rotation, then that what kind of motion? That's be linear, right? So what is orbit? Orbit is linear. It's a linear motion. Like here, just this is 0, this is R. Let's say this R, whatever you use, R1, and just move between 0 and R1, right? So that is, and then you can see here, when at 0, E equal to V prime equal to, so that is R dot equals 0. Then increase, right? Because, R dot is difference here is biggest. The increase R until here, the R dot is 0, right? So R dot equal to 0 at R equal to R1. So this is a turning point. So that means at this position turn and stop and then come back. So this is kind of the oscillation when there's no angular momentum, that is L equal to 0. Okay, so far we have 3 types of the force, then we have discussed the different type of orbit or motion depending on the initial angular momentum and initial energy. Now, we just analyze what will happen, either open orbit or closed orbit. So we have some qualitative analysis. Now we want to go to the details. We are going to see, okay, we have this orbit here, but we want to have now next job, right? So next job is how to get this, the exact or analyze the formula or the orbit. This is the orbit, right? Functional orbit, right? So that is orbit means or orbital equation, that means R as a function of theta. So we can see with a change theta what kind of orbit, either it's open or closed or circle or linear, right? All depend on how to open this one. So how to obtain this one? Then we are going to find this equation to solve this, right? We are going to look for the equation. Now we are going to looking for the equation of for this, right? Orbit. Function of R, variable R as a function of theta. We are going to looking for this. If we have the equation, then we can solve and get the formula, right? That is our next job. Okay, how to do that? First, either we get this differential equation or the integral equation depend on from a Lagrange, right? So now that's first. First, we are going to derive differential equation. Differential equation for orbit. How to do that? Of course, from a Lagrange equation, right? So if you remember from Lagrange equations, we have two variables r and theta, right? Remember we have two general coordinates for r. We have the, if you remember, we already have this, I think I already derived, so I just use the result. If you do not, let me take that. Just remind you, so we have the Lagrange equation for r, right? This is for r, and we have Lagrangian, so we just do this, and then we have this one. Give the result is mr double dot minus mr theta dot square plus partial v partial r equal to 0. So now let's say this is equation 1. Second, for theta, the Lagrange equation, we know that dt partial L partial theta dot minus partial L partial theta equal to 0. And we know theta is cyclic. We already discussed. So this one immediately gives us this conservation of the angular momentum. So that is m r square theta dot equal to L. That is equation 2. Right? So we have these two differential equations. Now we are going to combine this together to find, because that equation are function terms, right? So r dot theta dot dr square dt square or d theta dt. Now we are going to eliminate the t and get the function. Our goal is from this two to get this the differential equation for r as function theta. That is a differential equation for orbital, right? So that is our goal. Now how to do that? Okay. How to do that? There are, let's do the first here. Okay, let me combine these two together and then we can go to next. Since now we combine, we are going to substitute theta dot from here. Theta dot is L m r squared, right? So we replace this one to here. Then that equation is only for r, right? So now we have m r double dot minus, do we have a minus? This is minus, right? M, so now here we have L square m square r to the fourth power. We have, I think here is, yeah, it's r. So then become r cubed, right? And the others, others are same. M cancel. This is m square, this is m. So we have immediately got this, and that is a centripetal force, which is L square m r cubed, right? And equal to the, and then plot this one. I'm going to move it to the right hand side. So that is equal to negative partial v partial r, and that is centripetal force, right? So that is equation, if I say equation 3. Now we are going to, the goal is try to replace this one, dr squared dt squared by dr d theta. So how to do that? Let's do this one. Dr double dot is dr, let's see, is dr dot dt, right? And dr dot, now this is, I'm going to replace the variable, that is dr dot d theta dt. They are going to multiply it, right? So then this one is theta dot. So here we are going to use the theta dot here. So I put the theta dot in front, so that is L m r squared and dr dot d theta. But here still r dot is still time, right? So we keep continuing. L, I think we have no square, right? M r squared and d, okay, let me keep d theta. So dr is dr d theta dt. Again. And again, this is a theta dot. Right, so we replace theta dot, so now I'm going to repeat here, d theta, and that theta dot is L m r squared, and dr d theta. Be careful, since r is theta, I cannot take this outside, right? Be careful. This is a d, this term, so that means r is also function theta, so I cannot take this term outside, right? Keep it. Okay, so then but the constant I can take outside, so then I have L squared, m squared, r squared, right? This one, and d theta, and inside is 1 over r squared dr. Now you can see I replace double dot in terms of theta. So now I'm going to substitute this into here. Right? Okay, now let's do m. And here, since m, let's immediately, you see here, m, there's an m squared, so that is L squared over m, r squared, right? Immediately got this. And then there's a d theta, 1 over r squared dr d theta. That is first, and then minus L squared m r cubed equal to minus this one, but I'm just equal to fr, right? Okay. That is, we call this a differential equation, so that is differential equation for volume. That in principle we need to solve this, and of course depend on this. So how to solve it is not easy. Well, let's keep it. We will not solve it immediately. We are going to discuss or extract some information before solving this. So that is the equation here, but we can also replace r, u by 1 over r. Then this one became a little simple. So now if we replace this one, then you know du is negative 1 r squared dr, right? It's minus u squared dr. So then you have, so from here, we have to calculate dr, since we want to replace this one, dr, right? So dr is minus 1 over u squared du, and the du dr is minus u squared, right? From this relation. So we are going to substitute into this formula. Then we can have this equation for u. Okay. So here also this is also 1 over u. This 1 over r squared, r cubed is u cubed, right? So let me just to save time. So this equation replace u. Then we have this one. Okay, there are several issues. So this one here we need this, and this one is this u squared, right? So here this is a u squared. This 1 over r squared u squared. This is u squared, and this one is this, and so that's replaced. And this one is u cubed, right? And then so now we have minus, let me do this one, minus L squared m u squared d squared u, yes, wait a minute, here we have one term. Yeah, let me do this. So here, the first term is L squared m, r squared. That's this one. L squared r squared and d theta 1 over m r squared dr d theta. That became L squared u squared, right? This is L squared u squared d theta u squared over m And then this one, right? dr is minus 1 over u square du. So here, this u square will cancel. Then m I can take outside, so then you can see negative L square over m. Here u square still keep it, right? And d u square d theta square. Sorry, I think I have, this is a d theta. This d theta. So that is the first term. This is the first term, is this one. The second term is simple, right? L square over m q is L square over m u q. This one, fr is minus partial u partial r, right? Now we are going to replace by u.
6 hours.
So that is negative partial v, partial u, partial u, partial r.
You just start.
Or du dr. Then here that is negative partial v, partial u, and partial u, partial r here, right? That is minus u squared. Okay. So that totally is u squared partial v, partial u. Now we have three terms. So now we combine together. So we have, this is minus L squared over m, and u squared d squared u d theta squared, and minus L squared over m u to the q, and then the left hand side is here. This is a u squared partial v partial u. Or we organize by multiply this term both sides, so we have a d squared u d theta squared plus u, since you see this is cancelled, right? And u squared, so the plus u, they are negative, so and then go to this one is equal to negative divided m L squared, right? And this u squared, this to cancel partial u, partial u. We are going to use this formula. So I'm going to say this is fourth one. Now, so we have two alternately, another alternate differential equation in terms of u. And that is, if you look, the formula is simple, it's easier to look than this one, right? So that's why when we do the analytics, we're going to use this one. And you can also see here the symmetry of orbits. Whatever is open or closed, we know the orbit always symmetric, right? So if this is theta, this is negative theta, that is open circle, and if we need, you have R, this is R1, this is R2, so here theta and negative theta. So they have a symmetry. The orbital has symmetry, therefore, we will solve this. So we are going to just consider this theta in this range enough. We don't need this from 0 to the 2 pi, right? From 0 to pi, that's enough. So for example, from 0, and this turning point, and then we keep continue, and at second turning point, then the remaining part has a symmetry. So what we want to see is that if you have the solution, just solve this from 0 to pi, that's enough by the symmetry. That is analysis of this equation, what kind of orbit will give us. All right, so that is the differential equation. Now, we can also have another formula which is also very important. We call the integral equation. So that is our goal, right? We are going to find this differential equation for the orbit. Now, second, we are going to find the integral equations for the orbit, different formula. Either do the integral or do this solve this different equation. So the second integral equation for orbit. How to get this? If you remember the integral equation for this the r dot theta dot from the Lagrange equation, that is we use this conservation of angular momentum and conservation of total energy, right? Two conservation give us this from the second order differential equation reduced to one first order differential equation, and that is integrable, so we call this integral. So first, let's see this conservation of angular momentum. That is, if you remember, that is this one, right? R square theta dot equal to L. So that gives us d theta dt is equal to L or mr squared. Okay, and this one, keep continuous dt and multiply, right? So dt, this one, since we are looking for the orbital, right? So we are looking for the function r and function theta. So that is m r squared over L d theta. I'm going to say this is the equation. You got separate, so now I'm going to renumber this. Right? So that's equation 2. Sorry, equation 1. This is dt as is equal to this, and if r is function theta, so that is this one. Then second one, from conservation of the energy, right? Conservation of total energy. Okay, if you remember this, we have a total energy E equal to the linear radial part kinetic energy plus the angular rotation, right? So that is half of L squared m r squared. That is the potential for this angular rotation and then potential energy. Right? That is this. And from here, we obtain the r dot, if you remember. We just move this to the left-hand side and then take the square root, right? R dot is dr dt is equal to square root n over 2, and the energy minus, move these two terms to the left-hand side, right? Minus half of L squared n r squared minus v. Then dt, so this is a function of r, right? So this is all function of r. dt equal to, I multiply, right? Equal to, divided, so dr in the denominator, L squared minus v function r. So now I give us another equation 2. Now you can see the equation 1, equation 2, the left-hand side all are dt. Right-hand side are function theta, r is function theta, or r function r. So that E equal to 2, right? Equation 1 equal to equation 2, because both sides is dt, right? So then we have m r squared L d theta equal to dr Then the left-hand side is theta, the right-hand side is r, so I move this to the left-hand side, so I'll have the theta equal to the r. So I multiply this term both sides, right? Or divided this term both sides, so this is become L m r cubed, r squared dr 2 over m minus L squared 2 m r squared minus dr. Yeah. Or you can keep this by outside, but put this inside. And you have just follow the dr. So r squared is here and put L over m, so that we have L squared, m squared, but then in the denominator is m top and the L bottom, right? So then we have 2m L square E minus minus L square 2m R square minus B. Now I'm going to say 3. So this is the integral. Okay, we can do the integral now. This is a d theta, right? I can do this part since we are going to discuss this one first. So finally, if I do the integral both sides, this side, d theta from theta naught to theta, then correspond to r naught to r. So I have theta is theta naught plus r integral from r naught corresponds to theta naught to r, and 1 over r square, then dr, okay, and so that is 2m over L square energy minus this term minus 3r. This is called integral equation for orbit, if doable. Now the remaining part is, okay, sorry. So in principle, this will give us theta as a function of r, right, to the r. Then we come with the inverse so that we will have, in principle, we can do if it's doable. Right, so now we are going to discuss how, even before to solve that, how to analyze or extract more information from here. Sorry. So if alternately, if we still define u with 1 over r, do the same thing. So I just to save time, we will have theta equal to theta naught plus, then r naught corresponds to u naught, and r corresponds to u. Then we have, okay, that's a minus. I just save time, so I think you can do yourself to substitute this. And dr, we have already dr du, right? So that is minus, we have negative sign. And du, okay. Now you can see here, this 1 over r squared disappears. So that is, when we use u is better to do the integral or solve this. Okay. E minus, a minus, this one also has this, you see, 2m cancel, L square cancel. This is only u squared, right? So that is minus u squared. If we say that is equation 3, and I'm going to say this is equation 4, equation 4, right? So, in the remaining part is, if we are smart enough, we can solve this mathematically. You learn mathematics physics, and probably you also know that it's not easy. The difficult is this one. We do not know the formula, right? It depends on the potential. So which type potential, if constant, I think it's easy to solve, right? If not constant, it is difficult. So we will not discuss how to solve this. This is out of our class. We are going to focus on this physics, right? So now what we are going to do is the possible, let's just only focus on the power law. Function for the force. So if the force follows the power law, what this means, the force is R minus equal to negative partial V partial R, right? If this is proportional to the R to the nth power, that gives us the V as a function R speed proportional to the R to the N. yeah, negative r to the n plus 1 part, right? And n may be negative, may be positive, maybe fraction numbers, maybe integer numbers. So that is generally called the power law. So in this case, then we can discuss, again, even this case is not easy to solve. Only if you are a programmer, you can do this in numerical calculation, try to solve this and get numerical solution. That is possible. Otherwise, analytically, it is not easy. So, okay. Okay, I'll just stop here. So that is if we are focused on this type of so-called power law of the force. Then what we are going to see is the possible solution. Is there are several cases. One, for n equal to 1, minus 2, and minus 3. So the solution is the r theta is kind of a trigonometric function. So that is trigonometric function. Trigonometric function is circle and ellipse all are included with. So second case, if for n equal to 5, 3, 0, minus 4, minus 5, 4, minus, those are all integer, right? So the possible solution is, in this case, is elliptic function. For sum of, that means say sum is not all. For sum, the fractional exponent. So for this case, the solution of r theta in general is hypergeometric. Function. Okay, you see, even restrict to the power law, it still have difficulty. It's not easy to any solutions. That's just still for some of a particular case we can solve. So now we will not look this the detailed solution for those. What we are going to see is we are interested to try to find or extract information from this behavior such that, okay, not question, next question. What is condition to such that the orbital is circle? So question is try to find the condition for a circle. Circle means closed, right? So closed orbit for a circle orbits. That means you see here, we are going to discuss this power law. And n here we have no restriction, right? As I said, no restriction here, and only for some particular n we have a possible solution. Now, get rid of that, we just consider, okay. So if the circle means this closed path, right? That is stable orbit. So we are looking for the conditions for which n such that it can have this possible to form this circle orbit? That is next question. And that next question also, answer this one is not easy. So we are going to spend a little time and I make the copy for this supplement for detail, right? So the key is here is those can also get this circle or stable orbit, right? That is our goal because we want to see this orbit is stable. So for the stable, okay, that means what kind of circle? You should remember to get circle means r dot equal to 0, right? So in this case. So r dot means equal to 0 means partial v prime, partial r naught is equal to 0, right? Extreme. So that means if either this case, right, that's the prime minimum, then correct if it is at this position with the energy equal to this gives circles, right? That is for this power F R proportional to 1 over R like this one. Second case we have this one. We have a V prime maximum. And in this case also circle, since here this one also extreme, right? But then this force is proportional to 1 over R to the fourth power. Third case we have this case, right? V prime, and we have R naught here. That is another V prime minimum. In this case, force is proportional to negative. So this n equal to 1, right? Power. This n is equal to minus 4. This n is minus 2. So now you can see here. Minus 2 here, 1 here, minus 4 here. Okay, so now we are going to look what kind of condition, which n such that it is possible to get this circle orbit. If a wheel with circle is an ellipse, right? So that means, okay, let's first start this. So at r equal to r naught, this is a circle. What is condition we know? First, we have the equal to 0, right? And 0 means what? That means f prime r equal to 0 at r naught, right? Because f prime is negative, right? Negative partial v prime with r is the force f prime, and then if extreme is it is the speed, the first order derivative is equal to 0. Either this one maximum or minimum, right? So that is this case. So if this, and you know this f prime equal to f at position r and plus L square n r naught q, right? Equal to 0. So that gives us the real the centripetal force at this position equal to the circle. This we already discussed before. Is equal to this one. It's just equal to the centripetal force, opposite direction, right? So that is the first condition here. And I think others is not, we don't need to use them. Just skip. Like others, the angular momentum and the energy, you just substitute that into this R naught that you have. Okay. So now, what we want to see, stable. If a stable orbit, we need the second order derivative, right? So that means if we have a derivative of the energy from the equilibrium, so that is delta E, in this case positive, and in this case delta E is negative, and in this case delta E is positive, right? So what that means, we also mathematically know if we want to have a stable, that means to be minimum. So that the second order derivative of this one should be positive. right? N stable. It's negative. So what we are going to do is we are going to check. We're looking for this condition, right? So we're going to find the condition for the second order derivative of the v prime respect to r and r naught, which condition will give us this positive. So that is not, and then from there, we can give us the condition for A. Okay, so now let's do that. So now let's do this, just do this, right? So now let's partial, let's say partial second order derivative of v respect to r, then r equal to r naught is equal to negative partial f prime partial r, right? Because you see the first order is just negative. So that means, and f is this one, right? So that means negative partial f, the real pose, then r equal to r naught. And do this one, here we have a negative sign. So when we do this with respect to r, so we have a factor 3 here and go to r4. This negative, negative became plus, right? 3l squared m r naught to the fourth power. That makes sense? I do this, I have a negative sign. But here I have another negative sign here. So negative became plus. Okay. So we require this be equal to larger than 0. That is our condition, right? Okay, now, so now let me put this one. So partial f partial r with r to be r naught. I'm going to move that term to the left-hand side to be larger than negative, which is 3 l squared m r naught cube, right? 4. Okay, and that equal to, see here. Okay, so that equal to 3 l squared s squared over 0, right? So now the f r naught divided by r naught, right? This is the cube. This is to the fourth part, right? Okay. Wait a moment. Larger and negative. Okay. Plus, yes, plus. All right, so plus. So now here. Now let's go to the post, right? So the post is power. Let's say whatever the coefficient, right? So the partial f, partial r, when r goes to r naught, is minus nk r naught n minus 1, right? Okay, and then this f r naught is minus k r naught to n's power, right? Okay, so now let's get the left-hand side is minus k nk r naught n minus 1. It's be larger than 3. Then this one is minus k r naught to the nth power divided by r naught. I think that somewhere I have a sign with, let me see. Partial, this is an n, that is negative. This one, and then here, this is a negative, 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 negative. Let me first cancel those. I think I have somewhere the negative sign is, okay. That is negative partial. I think that is why I made a mistake, right? This be negative. I move this term to the left-hand side, but this one's the negative sign. I think somewhere across. Okay, so that, then here, so that is plus, right? So you can see the cancel, then the n is be larger than minus 3. That is the first condition. They only say the n is be larger, so that you see here. These are not. Those are cannot get stable, and that makes sense here. This is one example, right? Then of course so here 1 minus 3 minus 2 minus 3 4 and 5. These are all possible. The next question is, are they okay? And the answer is not all of them. So next one is, this is the first question. So next one is n, they allowed n equal to how much? They just gave a range, right? It's how much equal. To do this, we need the differential equation. From here, we just use this condition here, right? This condition for circle to be this extreme and over second order derivative to be positive. So we have this. Now we are going to answer what is the exact number of n. To answer this, now we go to this differential equation. So here, if we use u, right, because this is simple, u plus equal to minus m or u squared partial v partial u, right? This is our equation. Now we are going to from here. So analyze what is solution for u and as a function theta, or what is allowed. So in order to do that, let's first define the left-hand side. This part is a function u, right? So j as a function u is minus m or u squared partial v partial u. We define that is a function, and then this function we can and then define eta, which is the difference between u and u naught. U naught is 1 over r naught at the circle, right? Here. So we just consider the fluctuation, right? See, there's a small fluctuation. If it's stable, then make this a closed circle. If this fluctuation is unstable, we will go to the open orbit, right? So we are going to see with this small fluctuation and solve this one to see what kind of possible solution. That is the next goal. And of course, we will not solve that. We are just still qualitatively discuss. So how to do that? First, do this Taylor expansion in terms of eta. Taylor expansion. We just do this approximation because eta is small. So then the j as a function u is at the zeroth order, right? U naught. Then plus the difference is eta, right? U minus u, so the first order is eta, and the dj du, the u equal to u naught, and the second order is 2 factorial and eta squared, the square j, u squared, u equal to u naught. And that's up to the third order. That is we need. Otherwise, we cannot get the solution. So that's up to here. U equal to u naught and high order. So let's do this. Then if we select this, you will substitute this into okay. Put that aside. So now let's first. What is u naught? U naught is when the u go to u naught, right? So that is for u equal to u naught case. So then do the equation d squared u naught, d theta squared plus u naught equal to j u naught, right? From this formula, because this is j, this term, right hand side. So if u is equal to naught, is this one. And then this one is 0 because it's a constant. So immediately we have this j u naught is nothing but is u naught itself. That is the 0th order. Okay. So for 0th order, now we can actually from here you can also get that d eta d eta d theta is d u theta minus d u naught d theta is u d theta, right? Because u naught is constant. So from here, then d, then again, second derivative. The reason why, so now we replace this one. So now this equation became a d squared zeta. This is became solve the solution for the solve this variable eta, the difference of this u with respect to the equilibrium or the circle. And this one u is still keep here, right? And then the j equal to j. Okay, let me say j. Let's just directly use this one, right? J. J u naught is u naught, right? So I just immediately substitute this one. Is here, right? So that is u naught plus first order eta is j u equal to u naught. Second order so now we are going to solve this. Now, I'm going to move this to the left-hand side and also move to the left-hand side. So this first two terms to the left-hand side. Then you can see here, u minus u naught is eta, right? So this eta and one have a eta. So in terms of eta, we have let me give you the result. Beta square eta equal to the second order. And I'm going to let you know what is the beta square we introduced plus third order. So now we have an equation. Did I give the number? So now I just see this equation. This is equation 1. And this is equation 2. Then now it's equation 3. So here the beta square we introduce, which is this one, which is 1 minus dj du, which is a constant, right? Here, u minus u naught is eta, and this term become negative, right? I take eta outside as 1 minus this. That is beta square, which is a constant. So we are going to discount. What is condition for beta square? Okay. Now the question, how much? To do that, we, by definition, right? So that is 1. We just do that. 1 minus du dj. J is here, right? J is here. So that is minus m over L square, and d du j is partial v partial u, right? That is this term. Then we can replace by minus plus 1 plus m over L square d du, and here I'm going to give you jump one step so that you know that. Okay, here partial v partial u is partial v partial r partial u, right? And then this one is negative false. This one, you can remember that is 1 over u squared, right? So that is here. Okay, then the remaining, you just erase this part so that keep continue. Then you can do, okay, so then you can do 12. This one, and first do this. So you consider this one still a function of u, it's still fine, right? You replace r by u, so this is this term and this term. So we have 2 terms. Then now 1, let me see, okay, 1, I just go to that one, m over u squared is this one, is here still. And then we have 2 terms. The first term is df du and 1 of u squared minus f, if I use r, 2 over u cubed. Then u equal to u naught. You see here, this is a part d, df du. Yes. So when we do this, we have u1 over u squared, right, this term. And then we keep this one to this. So we have up 2, we have 3, and then we set. Like that. Then the following, I also want to join something. Okay. Since this term is u equal to u naught, so we immediately got this one. Fr became Fr naught, this is u naught. So this term, if you remember, we have Fr naught L squared over mr cubed, right? So that is the key is here, this one. So now let me go to the next one is 1 plus still m over L squared. And here, since this is only do this one, right? So this becomes u naught. So we have a 1 over u naught squared in this term. And then the dfr, okay, du, when u equal to u naught. Now this term, it became of factor 2 L squared over m. Because you will see that this is also u cubed, and so u cubed could cancel. Then now is this term. So this term is also easier than equal to. Let me see the fact. Okay, so now we have a 1. So you see this cancelled, 1 and 2. So we have a 3. 3 terms plus m over u squared. Now df du, right? Here one of u squared and df du, we can have u naught squared and df du. Okay, still keep that one. Is df du, u equal to u naught. And here we still can use replace this one by this f. The false at the r naught, so that is 3 minus become u naught f u naught. This term, right? And then here I replace df r, dr, and dr, du, and u equal to u naught. So we still use this one. Is 1 over is minus u squared. So finally, final is a 3 plus r naught f r naught df r dr r naught. The sum of step you can do yourself, I think, so I jump. Yeah, then I can. Beta squared is okay. So what is this one? This is the beta squared. Therefore, we have moved this 3 to the left hand side, so we have this one. we have beta square minus 3, I move this to the left hand side, and then that equal to this one. And then multiply this r dr and divide it r naught, so that is okay, let's say this. Move this one to the left hand side. F r naught equal to d f r dr. Right? Then now I see this is f df, this is r dr. So I can have this result is beta square minus 3 dr r equal to df f. Then because this is a constant, so you can see this is log, right? So then we have a log f equal to beta minus 3 log r. Now finally, we found f, take the log concept of f, is sum of a constant and r to this beta square minus r minus 3, sorry. Is this. So what that means, if you remember, we said that f is proportional to r to this nth power, right? So that means beta square minus 3 is n. And n is being larger than minus 3. So beta square is be larger than 0. Again, here we didn't give the detail beta how much it is, but at least we know for the stable orbit, beta square speed always positive. And to determine beta square equal to what, and the answer is 1 minus 2. And I think 0 is because larger than 0, right? So that is only these two possible we are going to answer next Thursday. And that is the so-called the beta theorem. Then we will answer that question. There are two choices. And what is, okay, that is two potential. One is one will ask for, another is this string, right? Like hook. Okay, so let's keep here. And I think to discuss this is give you some of critical thinking. When we deal with some of the complex system, before doing the details, let's try to analyze some of the information which we can extract from this. Then we have some idea what kind of motion, at least we know in our mind, right? That is the goal here. Okay, it takes time to have some details math here, but I do not want to spend too much the details. So we just want to understand how to get these numbers, where they come from, and what is the idea we can use. All right, yes. Some of part I jumped, and that jump part will not go to the result. Like after this meeting, next time I will not. The theorem of, the Worley theorem, that is 3.4, I jumped. Just the same time. And that is also easier for you to understand. That proves the relation between this potential and the kinetic energy, average kinetic energy. There's some relation there. Okay. How are you? Good, good. I think your this semester when you finish your graduate?
No, next semester.
You still another semester. Good. And after that you will keep continue to do PhD or go back?
I don't know.
You don't know. Depend on your sponsor, right?
Then I Genial PhD. I